Now I am going to introduce the Frank Hertz experiment. So I am going to give a very brief introduction to this experiment, and later you need to study this particular experiment. Okay, so this is a very interesting experiment. It was proposed by Frank and Hertz, and the objective of the experiment is to verify the existence of discrete energy levels of an atom and determine the minimum excitation energy of that specific atom. So this is the experimental setup, where this is a vacuum tube, and in this vacuum tube, in our case, argon gas is there, and then we have a electron gun is here, so that here, due to thermionic emission, electron would come out from here, and then because of there is a grid that is kept at a positive potential with respect to this the filament. So what will happen, that electron, after electron is being ejected from the filament, so there is a small potential, positive potential, so that these electrons can come out, and it would be somewhere here. Now there is another grid, that is a grid 2, which is kept at a much higher potential. This is the potential that is with respect to the common and with respect to the grid 1. So what you will find, that this potential at a much higher potential, and that because of this G2K potential, what will happen, this electron gain kinetic energy, and it will be accelerated towards the anode. Okay, now there is, the anode is kept at a slightly negative potential with respect to the G2. So this is kept at a slightly negative potential with respect to the G2, so that when the electrons gain a sufficient amount of energy, only then they overcome this barrier, because there is a barrier. This is in negative potential with respect to this grid, this is in negative potential. So what will happen, that when electron reaches, suppose this is, I can give some name, that this one is X and this one is Y. So when it reaches the grid 2, that is the Y position, then by that time, during this distance from X to Y, it must have gained some amount of energy, because this is in positive potential, so it might have been accelerated and it gains some energy. And if this energy is sufficiently larger than this barrier, because there is a barrier between the anode and the grid 2, because anode is kept at negative potential, so if it is possible, then only this electron can reach the anode, and there would be a anode current that flow in this direction, because electron flow in this direction, anode current flow in this direction, and you will be able to notice it in the nanometer, whatever it is, nanoammeter, whatever it is connected here. So this is the anode current. So this current is the anode current. So this current is the anode current. Now you try to understand that what is this experiment. This experiment, if you look at it, it's a very simple experiment, that electron comes out from the filament, and then there is a positive potential, so that means that electron should not be accumulated here, it should not create a space charge, because then there is a positive potential here, so it can reaches to the grid 1, and then there is a much higher potential, because what is this value of, in general we set it to 1.5 volt, and this GVG2K it varies from 0 to 85 volt. So this is the 0 volt to 85 volt. So this range, this is actually the accelerating potential. So this is the potential, because of that electron accelerate towards the anode. But the interesting thing is that anode is kept at a slightly negative potential with respect to G2. Since it is kept at a slightly negative potential, only the electrons which has a sufficient energy to cross this barrier, they can cross this barrier, otherwise there would be no current. Now the point is that when we do the experiment, when we vary the voltage from 0 to 85 volt, this G2K voltage, whenever we vary it with a potentiostat, then what happens, that if I plot the anode current versus this voltage, in that case we get a curve like this. So we find that the anode current initially increases, it reaches to a certain point, then suddenly it falls, and then it increases to a certain point, and then it falls, and then it increases to a certain point, and then it falls, and you will find it repetition of this thing. Now the question is that why do we get this kind of a anode current for this kind of a setup? The point is that it has argon atoms here. So since it has argon atoms, so the electrons that comes out from here in this path, this is the path that is very important to us. In this path length, because here it is being accelerated, there would be scattering with the argon atoms. Now when the electron has a scattering with the argon atom, there can be two different types of scattering. One is an elastic scattering and another is inelastic scattering. Now when we start from here, so initially there would be only elastic scattering, because this electron's energy through this elastic scattering will not decrease. So the argon mass of argon atom is much larger than the electron. So in general what we will expect, that you don't expect that there is any change in the kinetic energy of the electron. So although there would be this kind of elastic scattering, but since it is in a potential difference and it is moving towards the positive potential, so what will happen, that it will keep on gaining energy. So during this trajectory from here to here, you expect that electron gain energy sufficient so that it cross this barrier and it can reaches the anode. Now what will happen, that if you keep on increasing the voltage, more and more electron will be able to pass this barrier, and then it can accumulate, it can move to the anode, and the anode current would be higher and higher. So that's why you can see that there is an increase in the anode current. But there is a point for a particular voltage. What happens, that when it reaches a certain voltage, that means when it gain a certain amount of energy, if this energy is equal to the energy of first excitation of that particular atom, then there would be an inelastic scattering. That means that electron's energy will be absorbed by the argon atom and it will be excited to the first excited state. So the electron would lose entire energy, and then what will happen, that if suppose the electron move this far and here it gains that much of energy that is required to bring the argon atom to its first excited state, then it gives that energy to argon, and argon moved to the first excited state and then it de-excited and it can be released as a photon of certain the same energy. But by that time what will happen, that electrons energy becomes zero. So if the electron's energy becomes zero, then this electron cannot cross this barrier, it is not possible, and then that anode current start falling. So if you keep on increasing the voltage here to here, so what will happen, that more and more electrons will gain the energy such that it can reaches up to the argon's first excitation energy, and then it loses all amount of energy and it cannot reach the anode, and that's why the anode current falls drastically here. Now what has happened, that because we are increasing the voltage, so voltage is continuously increasing, so it is enhanced. So if voltage enhanced, what will happen, that some of the electrons now they start gaining more energy. Suppose that this electron travel this much in the earlier case, and then by this, through this distance, it gain the amount of energy that is equal to the excitation energy of first excitation energy of argon. Now it may happen that when I increase the potential, the electron when reaches this much of distance, much lesser distance, this is much lesser distance, it gain the same amount of energy and it give it to the argon, and then electron's energy become zero, but then there is a sufficient amount of distance left so that it again gain that amount of energy to cross this barrier. So what will happen, that you will again see there is a enhancement of the anode current. It is just because that the voltage is such that in a much lower distance, traveling a much lesser distance, the electron gain the same amount of energy and then it give it to the argon, and after that there is a sufficient amount of length is left, and during that period it gains the energy to cross the barrier. So you will find that more and more energy will gain the energy to excite the argon atom, and then after that also, even if it loses the energy, but it will have sufficient distance to travel, and in this distance it will gain the energy to cross this barrier, and that's why you will again find that there is a peak. So once the distance is such that, suppose I just want to find out a distance like this, suppose electrons in this small distance it gain the energy so that it can excite an argon, that means there can be an inelastic scattering. So what will happen, it gain that amount of energy and it excite the argon, and then there is a sufficient distance. In this distance also it can gain the similar amount of energy and even it can give it to argon. So once it give it to the argon, that is almost at the level of G2. So here if it give the entire energy to the argon, then it does not have any distance to travel, and then what will happen, that suddenly this electron will, none of this electron will have energy so that it can actually cross this barrier. So you will find there is again a fall. So you will find such kind of increase of anode current and decrease of anode current. It is just because that as you keep on increasing this voltage, that is Vg2k, this voltage as you keep on increasing, the thing that will be interesting, that at a much smaller distance, electron gain the energy that can be given to the argon to excite it to its fast excited state. So now the if you just look at that, if I check all the minima or separation distance between the maxima and minima, if you find out the separation voltage between maxima and minima, and if you measure it, you find out that that is the amount of electron volt, that is the first excitation energy of the argon. So this is how one can find it out that atom has discrete energy level, because exactly when the electron get that amount of energy level, then only it can have an inelastic scattering with the argon, and the argon can be excited to its first excited state. But in this entire period here, what we will find that there would be inelastic scattering. Okay, in the second case, what we will find that there would be one elastic scattering, but after that there would be only one inelastic scattering, but after that there would be only elastic scattering, and here when it reaches, that means there are two inelastic scattering. So here two inelastic scattering, in this case it is one inelastic scattering, in this case it is three inelastic scattering. So you can understand that whenever the number of peaks means the number of times of inelastic scattering takes place. And the peak, another important thing is that the peak indicates that the inelastic scattering exactly takes place at the G2 level. That means after that electron will not get any because G2 is certain, it is kept at a positive potential, so up to G2 it can gain energy. So if here after reaching G2 or just before G2 it loses out all of its energy, then it will not be able to cross, and that's why there is a fall of current you can expect. Now the question is that you can see that even if the spacing is equal to the first excitation of the argon, but what you can see that there is a constant increase of anode current. You can try to think that why there is a constant increase in anode current, while every time you can see there is a fall of a anode current, and again there is a rise of anode current. Okay, so you will be provided with the data, and you need to plot this graph, and what are the else you need to do, it is written in the lab manual. Thank you.